All right, we're going to put together everything that we've been talking about in the last lecture or last couple of lectures dealing with the quantum model of the atom and all of those quantum numbers and kind of putting it all together to look at what is called the electron configuration of an atom. And this is just kind of a text way to show the arrangement of electrons in an atom. We're going to put all those trends together that I highlighted about how do you find easily on the periodic table the principal quantum number n, or how do you know what subshell an atom is in. And so just to quickly review that, by looking at the row, that's where we can figure out n. So n was based on the row the atom was in. And then we called, we had like these two columns, including helium, be our S block elements, and then these six, or I should say group of six here are P block, and then D block was the transition metals in here, and then F were these down here, our F block. And now we're going to kind of put that all together because we're going to start outlining like where are all the electrons. And what I'm going to do is a quick example, and then I'm going to go through step by step how we get there, all by using the periodic table. So there's going to be very little memorizing in determining the electron configuration. So I'm going to look at carbon here first. Okay. Now carbon has 6 protons. How do I know that? That's its atomic number. And assuming it's neutral, it should have 6 electrons. So where are all of those 6 electrons located? So the electron configuration for carbon is going to look like this. 1s2, actually no commas, we don't use commas in this. 2s2, 2p2. Now what do all those things mean? Okay, well, these numbers right here, the big numbers, that represents n, the energy level, the principal quantum number. Now, note what row carbon is in. Carbon is in the second row. Okay, so in order that means the electrons here in n equals 1 are on the first energy level. And then the electrons that are in 2 are in the second energy level, or the second floor. Notice that I don't go any higher than that because that's where carbon ends. Now, what are the letters? S and P. Well, that's the types of subshells the electrons are in. Notice what the very last subshell is. The very last subshell is P. Well, what block is carbon in? Carbon is in the P block. And then finally, what do these superscript numbers represent? Those represent how many electrons are in each of those orbitals. Now remember, one of the fundamental things about an orbital is no more than 2 electrons in an orbital. Remember, in the S subshell, there's 1 orbital, so it means I can only put in S total 2 electrons. In the P subshell, there are 3 orbitals, so I can put 6 electrons, up to 6 electrons in the P block, or in the P subshell. D has 5 orbitals, so again, I can only put 10 total, and in F, there's 7 orbitals. I can put up to 14 in those. Now, let's take a look at another kind of, this is a special, not, I'll say it's not a special type of periodic table, but kind of a template. This is more for electron configuration. And now you're going to kind of see how I got to carbon. So carbon would have been right here. I'm going to write that in. Okay. So I'm going to start all the way at hydrogen. Hydrogen would be 1s1. And then I'm going to read left to right like I do a book, a piece of paper. And then helium, 1s2. Helium has two electrons total. Both of those are going to go in 1s2. Then I'm going to go down to atom number 3, 2s1, and then 2s2. That's as much as I can put in the 2s. So then I go here to the p block, 2p1, and then here for carbon, 2p2. So when I write the electron configuration for carbon, I'm including all of this. 1s1, I'm sorry, 1s2, because that's full, 2s2, because that's full, and then 2p2. Now, one way to kind of check your answer is the number of electrons here should equal how many electrons that atom has. If those numbers don't add up properly, then your electron configuration is incorrect. So let's do some practice. All right, the first atom we're going to do is oxygen. So here's oxygen. Oxygen has 8 electrons. We're assuming it's neutral. We'll talk about ions in a little bit. But let's just assume for right now it's neutral. Okay, so I'm going to go left to right here, read the book, and that ends in 1s2. And then I'm going to go here. So notice I'm filling up the 2s2, and then I'm going all the way here, four places, and so that ends in 2p4. So let's write all of that. 1s2, 2s2, 2p4. And notice all of these three numbers right here add up to 8, so I have the right number. I have the right electron configuration. Now let's get a little bit more complex. I'm going to erase all of this, and let's do this for phosphorus. So phosphorus has 15 electrons. How do I know that? Assuming it's neutral, since the atomic number of phosphorus is 15, has 15 protons, it's going to have 15 electrons. And again, all I'm going to do is read from left to right, top to bottom. So I go left to right. Okay, that ends in 1s2. I start on n equals 2 here, and that ends in 2s2. Then I go to the p block. That's 2p6. Okay, I still haven't gotten to phosphorus yet, so I'm going to go to the next row. Here, that ends in 3s2. And now I get to the p subshell, and I get to phosphorus, and that ends in 3p3 because it's 3 spaces over. So let's write all of that in. 1s2, 2s2, 2p6, 3s2, 3p3. All right, so those are just a couple practice problems. I highly encourage you, like, pick an element. And right now, if you're going to stop and practice, just do 1 through 18. Just pick any of the elements there, and just practice this. We'll get into like the D and the F subshell. When we get into this D block, it gets really weird. Again, um, you know, there's going to be some interesting oddities that happen when you're dealing with elements in the D block, or what we call the transition metals. But before we end this part, I want to look at another way to notate kind of electron configuration, and that's to actually pictorially show all of the electrons. So we call these orbital diagrams. This is just another way to represent the electron configuration. So I'm going to start off really simple with helium. Now, if I were to do the regular electron configuration for helium, it would be 1s2. Now, the orbital diagram, what we're going to do is we're going to use a line for each orbital. And I'm going to put the name of the orbital under there, 1s. And I'm going to put the two electrons here in that 1s orbital. I'm going to put a half arrow up and a half arrow down. That's the convention. Convention kind of always does up first and down second, but you don't ever show them going both up because remember, electrons are going to have different spin quantum numbers. Like we said, this would be plus one half, that would be minus one half. So that's how we represent those different spins is by having one up and one down. Now let's do this for nitrogen. Again, let's start with just the regular electron configuration. So nitrogen's right here, 7 electrons. So we have 1s2, 2s2, and then 2p3. So the orbital diagram will look like this. Here's our 1s, here's our 2s. Now, how do we represent the 2p subshell? Well, how many orbitals are in the p subshell? Remember, the p subshell has 3 orbitals. Those are those dumbbell-shaped ones. And so now I'm going to start putting electrons in. I can only put 2 electrons in an orbital. So I'll put them in here, 1s. And then I go to 2s. And then I got 3 more to put in the 2p. Let me show you the wrong way to do this. We don't do this. Okay, and there's a reason for that. We must fill, or I should say half fill, degenerate orbitals before completely filling them. This is known as Hund's rule. Now remember that term degenerate? So when we have multiple orbitals that are equal in energy, like the 2p orbitals, we have to half fill them before we completely fill them. And we generally put them all in the same direction. So this technically would be incorrect if I did like one up, one down, and one up. That's not what you want to do. You have them all up. And since I'm out of electrons, nitrogen only has 7 and I've drawn 7, that's going to be my orbital diagram for nitrogen. Now let's do one more example. Let's do fluorine. So again, I'll start off by doing its normal electron configuration. So we go left to right, we hit the 1s2 filled up, and then we go to the next row. Now the 1s2, or I'm sorry, 2s2 is filled up, and then I hit the 2p, and I go 1, 2, 3, 4, 5, and there's 5 electrons in the 2p subshell. So let's do the orbital diagram. I have 1s, 2s, and 2p. So I'm going to fill up the 1s with its 2 electrons. I'm going to fill up the 2s with its 2 electrons. And now I'm going to fill up what I can with 2p. So I'm going to half fill everything. Okay, that's 3. I got to put 2 more. So now I can start filling them until I'm out of electrons. And that's how we do orbital diagrams. Again, it's pretty much the same as electron configuration. It's just we are drawing all of the electrons showing them exactly which orbitals they are in. Now, before I conclude, I want to show you this cool website, ptable.com. And this gives, if you when you log onto this website, go right up here to electrons. So it starts off looking like this. But if you click up here on electrons, you can actually click on any of these atoms and it will show you the electron configuration. So like I'm going to click on lithium here. So lithium, it shows you 1s2, 2s1. Trying to get Zoom to notate, it won't let me notate. Okay. Um, or if I go here to say aluminum. So aluminum, you got your 1s1, I'm sorry, 1s2, 2s2, 2p6, and then I'm going to go 3s1 and then 3p1. So this will be a great resource to kind of practice, maybe pick an atom and then try to do its electron configuration, and you can check your answer. So I guarantee you, on your assessment, you're going to have to do electron configurations and orbital diagrams. So make sure that you know how to do this. In our next video, we're going to look at some of the weird things that happen when we deal with the elements in the D block.